Welcome, this is Dr. Hisham Said. In this video, we'll go over trying to visualize how shear stresses develop due to torsion loads in shafts. So let's see here an example of a shaft that has cross-section with radius C, and I can draw here the XYZ coordinates following my right hand rule. So X, Y, and Z. So X, you can see it, X, Y, and Z. Try to make sure that the axes here following this right hand rule. At any point, I will define this point with radius rho. And this shaft is under torque. This torque can be a load, or I can actually do a cut at this point, and this will be the internal torque I can figure out with statics. And we learned from a video that I posted from Structures Free. It's a very awesome video. That the shear stress due to torque is equal to T rho over J. And if we follow that formula over any point that has a radius rho, this means that the shear stress is linearly changing with rho. So the farther away I go from the center of or the centroid of the cross section, the larger the shear stress will be. And we also learn in this Structures Free video that the direction of the shear is dependent on the location of the point, so it will be perpendicular to the line or the radius of this point to the centroid. We'll discuss more on that in just a minute. And we see here tau max, the maximum tau. I cannot go forever because rho doesn't go forever, so tau max will develop at the maximum value of rho, which is here will be tau max. So tau max will be at the maximum value of rho, which is actually C, so the outer diameter of the shaft. And then the other thing I want to highlight here is also J, the polar moment of inertia. So it's equal to, for the shaft, solid shaft, pi C to the power 4 over 2, or for a hollow shaft it will be as shown in this formula. So just pay attention to what case you are. Don't be confused by saying C1 minus C4 all to the power 4. So it's C1 to the power 4 minus C2 to the power 4. Now, how the shear stress will be over different points or the whole cross section. If this is kind of a looking projection of the section, and you see here, every point will have a direction for tau dependent on the geometry of the section, also that this tau will be perpendicular to the radius of this point. So the left point will have tau max pointing down, the right point will have tau pointing up, the upper point will be having tau going left, because all of that is following the direction of the T, the torque. So tau follows the direction of T in the perpendicular direction of the radius, connecting to that point from the centroid of the section. So if I now kind of pick a point at this rho radius and represent it with a stress block. So if you remember back a couple of videos back, we discussed the idea of having a general stress state in a 3D block, and this is what I'm trying to do here, figuring out what are the stresses applying at this point, but projecting them or putting them on a 3D stress block. And the face that's to the right, that's where X is popping out, is the one that's representing that little point on that section that I'm showing on the bigger drawing of the shaft. And tau at this point is actually going down, negative, in the negative y direction. And the surface of that block that I'm drawing on is perpendicular to the x, which is the same surface of the cut that I'm analyzing here for the whole shaft. And we learned that I can also draw a 2D projection of that 3D block. So I'm now looking through the z-axis, and I see now x going to the right, y going to up, and this tau xy that's developing here. And one thing I want to highlight also, that this tau that's developing from this t is called tau xy also. So it's on the face or the surface is perpendicular to the x, so tau x, and then it's in the direction of the y-axis, so it's tau xy. So that shear, the point here, it doesn't exist by itself on that surface. So if you look at the stress block, you will find that for equilibrium purposes, you will find there is a shear stress developing on the opposite side of the block. Or if you can think of, if I did a cut at this point, but then dealt with the right side of the cut, not the left side as shown in the shaft, then the shear will be developing going up. And another thing is, these two shear now, tau xy, they will cause a couple moment. So to resist this couple moment, I will have a couple moment opposite to that, that's created by shear forces or shear stresses on the top and the bottom surfaces of that block, which we call longitudinal shear. So tau xy is a transverse shear because they have this transverse action or torque, and then the longitudinal shear is developing as shown here on the block, and that's developing because there is longitudinal shear. So that was kind of a review of the video you have watched, or I recommend watching, from Structures Free. It's a very good video, but kind of trying now to build on that and understand that the directions of this shear stress that's developing at a point, and representing that shear stress direction on a stress block. So that strengthens our understanding of shear stresses and how they develop due to torque or torsional loads. Thanks for watching. We'll see you in other videos.